Good afternoon and welcome to the ESAB Specialty Alloys live event. My name is Clemente Talarico, and with me as the presenter we have Mr. Peter Stones, as well Mr. Per-Åke Bjornstedt for technical support. I'm pleased to announce here the 7th presentation of ESAB Specialty Alloys, which will happen every third Friday of the month at 14:30 European time via Teams live event. The 7th presentation of the program will be the one starting in a few seconds with the title How to Improve MIG Welding of Duplex Stainless Steels. We will be very happy to answer your questions at the end of the presentation, which you can type in the Q&A box you will find on the top right of your screen. We will intend to present on about 30 minutes and take 10 to 15 minutes more for answering your questions. And so, with that said, and now let us start the show with Peter presenting. Enjoy.
Thank you, Clemente. Good afternoon, everyone. As Clemente said, we'll be taking about 30 minutes. So it's more to give bullet points, some pointers on the subject that we're talking about, improving welding of duplex stainless steel. We're more than happy to let people have copies of the slides. Clemente's and my contact details will be given at the end of the presentation. Please feel free to contact us if you'd like a copy of the slides. And the Q&A is done via the Q&A box that's on your screen. We'll do our best to answer what we can. If we can't, then again, if you can send us drop us an email, then we'll do our best to answer as soon as we possibly can. So the topic of the talk is improving welding of duplex stainless steel. So how are we going to do that? What I want to talk about really is to recap on the history of duplex stainless steels. What are they? Where did they come from? This new grade, this unique grade, duplex LSI. So why does it differ from standard duplex grades? For any kind of change of grade, welding engineers are always concerned about the AWS and ISO classifications. We'll discuss them. And what does the silicon do, the additional silicon, what does it do to the properties of the weld metal? Why do we go to all this trouble? What are the benefits? And then we'll go into some success stories right at the end. So, what are duplex stainless steels? Well, it's a mixture between austenite and ferrite. There's a duplex structure. In the micrograph, you can see the white marks, the white areas rather, are austenite, and the darker lines are ferrite. So in this, we've got a nice duplex structure, 50-50. The benefit of mixing the structure like this is that it gets the best of both worlds, really. It gets much more added strength. So the yield strength of a duplex is very much more than a slightly ferritic austenitic stainless steel such as 316, and I'll show that in graph form later. That's the reason that the duplexes were developed. The properties are that the chemical resistance, the corrosion resistance, and the mechanical properties are very much better than standard duplex steels. So it originated from the Latin word twofold, duplex, that's what it means. First commercially available in 1930, so not that long ago in metallurgical terms. So on looking at a timeline, this split between 1970, the first generation, these are grades of duplex that were produced and were commercially available, but they were not weldable, so we're not interested in them. The second generation are all weldable. The scale that we're looking at here is PRE, pitting resistance equivalent number. So that's a measure, if you remember, it's a measure of the corrosion resistance, and specifically corrosion resistance to pitting corrosion. So you use the composition of the grade in the formula and come out with a number. There are no units on it, it's just a number. And this is how we rank the various grades within the duplex family. So from lean below 28, the PREs below 28, duplexes are up to around about 40, Super duplexes are 42 and above, and then Sandvik produced this unique thing called hyper duplex, which is above 49. So it's a rank. It's a number that's always associated with stainless steels, and it's very important regarding duplexes. So what do the various elements do in the duplex stainless steel? Why do they go to put chrome, nickel, moly, nitrogen, blah 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 into them? The chromium is the key element that's responsible for creating the protective layer. The chromium reacts with air and produces chromium oxide. That's what gives stainless. That's what makes stainless stainless. It gives its passive corrosion protective layer. Molybdenum is always associated with corrosion resistance. Nickel is an austenitizer, which means that the ferrite liquid. The liquid stainless steel, if you like, when it's in liquid form, when it's welded, it's pure ferrite. When you cool that down, you want 50% of that to turn to austenite. Nickel in the composition will help that happen, as will nitrogen. Okay? Manganese is in there, and it's usually to reduce the effect of impurities in the steel. So it helps with things like oxygen and sulfur. And tungsten is an addition that's added into some grades of duplexes to assist in corrosion resistance. So the composition that we're looking at for the various grades, we're listing duplexes, this duplex LSI, as well as super duplex and the hyper duplex. So specifically, we really just want to look at the top two, the standard duplex. So it's Exciton 2283L or Exciton 2283LSI. AWS ISO, it's still a 2209. Okay, so the standard duplex, you can see that the silicon content is 0.5%, whereas the 2283 LSI has slightly more, but it's a significant amount. So what you will see is that the PR, everything else rather in the composition is exactly the same. Carbon, manganese, chrome, nickel, moly, nitrogen is exactly the same. It's purely got an addition of silicon in there. That's the difference. So why do filler metal manufacturers go to the trouble of making silicon grades? Well, grades like 308 LSI and 316 LSI, 309 LSI, these are fairly common in common usage. They've been around a number of years. And the reason for adding silicon in there is exactly the same in every case. It's an added deoxidizer. It provides good weld metal fluidity. The more alloys that you put into a grade, the more of these chromiums and nickels that you put into a metal, it means that the weld pool is much stickier. It's not as fluid, so it's not as easy to weld. So the reason that these kind of things were developed, the 308 LSI, 316 LSI, the reason that they were developed was to make them easier to weld. Better fluidity of the weld pool increases the wetting into the toes, so it kind of ensures more chance of a complete complete fusion, and produces a smoother and flatter weld bead, so it looks better. So the difference with the 2283 LSI is the first duplex grade on the market to have the additional silicon. As I mentioned before, it's got 0.8. So the effect that we see in the austenitics with silicon, for the first time, we're able to get the same kind of benefits with a duplex grade, a 2283 LSI. So in terms of ASME section 2 part C, these are the requirements, the composition of 2283 of 2209, I should say. These are the requirements of the composition of a standard duplex in terms of maximum values. You can see the standard duplex obviously meets the composition of ASME, and the LSI, even though it's at 0.8, which again is different from everybody else producing it on the market, is still well within the maximum permitted level of 0.9. So you can see the AWS reference is 2209. It's exactly the same as standard duplex. The ISO reference, 2293L, is exactly the same. So the LSI 100% conforms to the same specification for TIG and MIG applications. If the welding process specification states must use AWS 2209, then you can substitute a standard duplex for the LSI and it still conforms. It still says AWS 2209, and that's obviously what it'll say on the certificate. So in addition to all the composition is exactly the same, well, not surprisingly, the PRE number is exactly the same. Because the PRE is a factor, is a formula utilizing the composition, then because the composition is exactly the same and it doesn't include silicon, then the PRE number is exactly the same. So on the scale, showing you how a standard austenitic sits on the same scale. So 316L has a PRE of 24. And the difference is with duplexes, so both the standard duplex and the LSI version, they're at 36. So it's significantly more resistant to pitting corrosion than 316. And just to put it on the same scale, you can see super duplex and hyper duplex. So hyper duplex up at 49. In terms of mechanical properties, we've got a graph here of 316 versus standard duplex, LSI duplex, super duplex, and hyper duplex. See that the yield strength for the LSI version is exactly the same as the standard duplex. And again, just to illustrate it on the scale, 316L has a yield strength around about 200, and the duplexes, both of them, have a yield strength of 470. So it's significantly different. This is the benefits that are utilized when using duplex stainless steels. And on the same scale, we can see there's a significant bump up to super duplex and then an even bigger bump up to hyper duplex. In terms of weldability and fabrication, the duplex LSI version is treated exactly the same as standard duplex in terms of thermal expansion. Thermal expansion is a big issue if you're moving from carbon steel to something like 316. The expansion can cause a lot of problems, so you've got to be careful with your welding sequences, etc. But the duplexes, both the LSI and the standard L, act in exactly the same way. Next, I want to talk specifically about welding. Joint preparation, heat input, shielding gases, and what happens if you get it wrong. So what are the advantages of welding Exciton 2283 LSI? So in terms of joint preparation, the care still has to be taken before you even start welding. Care's got to be taken in the joint preparation. These things are higher alloy than carbon steels, and consequently, in spite of everything, the weld pool is not as fluid. To ensure that you get good fusion, no lack of fusion problems, then the gaps have to be wider than would normally be for carbon steel. The angles have to be more open than would normally be for carbon steel, and this is to compensate for the lack of fluidity. All I would say is that with the duplex LSI, it's better than the standard duplex. Nitrogen's an important element in terms of shielding and purging gas, and I've got a couple of photographs that illustrate that much better. In terms of MIG-MAG welding, we would recommend using an arc stabilizer. In addition to pure argon, use an arc stabilizer such as CO2 or helium. And with TIG welding, then nitrogen is very, very important, as you can see from these two diagrams. So this is 100% argon. And what we have here are areas of ferrite. So over here, we've used 3% nitrogen in the shielding gas. You can see that the structure all the way to the surface is very good formed duplex. It's a nice duplex structure. Over here, there are large areas of ferrite. So the properties of this bit on a micro scale, yes, but if this is across the whole weld, then there are issues, because this isn't duplex. This is mainly ferrite. So what it means is that these areas don't have the same corrosion resistance, and they don't have the same mechanical properties that you would expect from a duplex weld. Similarly, in the shielding gas, in the backing gas, in the backing gas, exactly the same effect. So if there is no nitrogen here, there's no nitrogen to turn the ferrite into austenite in the bottom of the weld. So you've got a very dark ferritic area. So this isn't duplex. So the properties here don't have the same corrosion properties, they don't have the same mechanical properties. What's the solution? Use purging gas, preferably 100% nitrogen, or certainly nitrogen with 10% hydrogen. Heat input, very, very important with all stainless steels, certainly important with duplexes. And we're talking heat inputs as low as 0.5 kilojoules per millimetre. An interpass, obviously there's a big range between 0.5 and 2.5, but the interpass is a given. Please don't exceed 150 degrees on the interpass temperature. What I will illustrate is that the LSI version, again, is exactly the same. Treat it in exactly the same as a standard duplex. And these are the reasons why. So if it cools down too slowly, if the weld is cooling down too slowly, and that can either be because there's too much heat input to start off with, you're exceeding the 2.5, or the interpass temperature is ignored. The welder has to get another pass on before he goes home, so he ignores the interpass temperature, so he heats this up far too much. So in cooling down, this is a TTT diagram, temperature over here, time on the x-axis. If the cooling rate is very slow, then you get difficulty in crossing these noses, which kind of illustrate where you start getting problems because of the temperature. Dwelling in these areas basically creates the precipitation of intermetallic phases. So sigma phase is probably the common one that most people have heard of. And what they are ferritic intermetallic phases, the black dots. And the black dots are areas of weakness. They're areas of ferrite. So these areas, these dots don't have the same properties as the surrounding duplex matrix. If there are too many of these, then the whole strength and corrosion resistance of the whole thing is suspect, is in doubt. So that's if it's too slow. If it's too fast, again, the welder needs to get another pass on, but he doesn't want to ignore the interpass temperature. So he pours a bucket of water over the weld, quenches it. And what happens there is that the crystals will freeze, and you'll get massive grain structure, massive grains formed in there. The thing with massive grains is that there's very few grain boundaries. Very few grain boundaries means this is very brittle. It just wants to break. And in addition to that, the sudden freezing will cause chromium nitrides to be formed. So you're getting chromium depleted areas. If there's no chrome, then the metal, the alloy is not stainless. So the chromium's precipitating out into chromium nitride. So the areas immediately adjacent are robbed of chrome. So they're not even stainless steel. Okay, so again, big problems with heating down too quickly, big problems with heating cooling too slowly. What we try and do is keep it in the middle of the road. If you keep it in the middle of the road, then we get this nice duplex structure. That's the reasons why. So what are the advantages? Why are we going to all this trouble and we're promoting 2283 LSI? So right from the beginning, we've always talked about the fluidizing the weld pool. This is the key. The silicon increases the fluidity of the weld pool. The fluidity of the weld pool means that it'll flow into the toes, it'll flow into the root gaps. So lack of fusion should not be an issue. So failures, essentially failures that will get detected at NDT, should not be an issue. Obviously, for the welder, if he's welding this and he's getting a nice fluid weld pool, then it's a lot easier to weld than trying to push chewing gum into the root gaps, for example, which is what high alloy filler metals are like. They're more like chewing gum than a liquid. So it's more difficult. It's more difficult. It takes longer. It takes more time. There is a strong possibility of not being able to get into root gaps, for example, especially, you know, there are occasional areas where the root gap's not quite right. The fit up's not perfect, so the root gap's not as big as it should be. It's going to cause welders headaches, and ultimately, it's going to cost money. It takes time, and it's going to take reworking. We have documented projects where we've proven that for automating TIG welding, we've improved the productivity by 17%. So the fluidizing the weld pool mean we can turn it up. We know we're going to get a good penetration. We know we're going to get a good fusion. We're going to get the weld metal flowing into the roots. So you can wind things up. You can wind up the speed, so up to 17%. And then really the next three, spatter, post-weld repairs and surface residues, they're all to do with cost savings. So this is a low spatter product. The amount of cleaning up after this has been welded is significantly reduced. It's a very low spatter filler metal. So if we're not getting spatter, we're not getting surface residues, we're not getting lack of fusion, then there's ultimately less post-welding repairs. So we're talking about saving. We're talking about saving money on just speeding up, or speeding up in that you don't have to spend time grinding. You don't have to spend time doing post-weld repairs. And another thing, another aside, is that for the corrosion test G48E, the critical pitting temperature of this alloy, 2283L, is 37.5, whereas a typical competitor's product for standard duplex is 32.5. That's a significant difference if you're trying to consistently pass a G48 corrosion test. These are customer trials. They were trying a standard competitor's 2209. They were comparing it to the Exiton 2283L, so this is our standard duplex, and then ultimately comparing it to the 2283 LSI. So you can see the condition, the rough surface of the finish, the toes on the regular 2209. The whole weld looks a little bit discoloured and not as smooth and as nice as it could be. With a standard Exiton duplex 2283L, I think they're a little bit better. Things are a little bit better. It's a little bit cleaner, a little bit tidier. If you move over to the 2283 LSI, then you can see that the weld pool is very much smoother. It's very much smoother, and it looks a lot flatter, certainly compared to the regular one over here. So the weld bead is smoother, flatter, and generally the whole weld looks to be better. Its appearance looks better. They were very happy with that. In terms of troubleshooting for welding, this is a table I don't propose to read every word, but if you're getting with sigma phase, there are fairly standard causes and solutions for it. If you're getting too much austenite or too much ferrite in your weld, again, there are very standard causes of this and standard solutions. Failing corrosion tests, yeah, again, failing bend tests for dissimilar joints. If you get a copy of the slides, then you can read these at your leisure, no problem at all. So moving on to applications of the 2283 LSI. So obviously 2283 LSI is the filler metal. Okay, it's the filler metal for welding duplexes. So people that are manufacturing products from lean duplex or standard duplex are utilising the LSI to make benefit of the faster, better, smoother, improved welding quality. So these are two examples, both transportation, you can see, tankers. There's a number of customers around the world making tankers, whether for milk or fuel or sugar, whatever, making them from lean duplex. And the idea being that because of the high mechanical strength of duplex, then you can reduce the thickness. If you reduce the thickness, you reduce the weight, which is the key to all transport problems. So they're starting to manufacture tankers like this, road tankers from lean duplex, and they're welding them with the 2283 LSI. Similarly, we've got at least two train manufacturers that are, again, they're using standard duplex rather than lean duplex, again to save thickness, again to save weight, and again they're welding them with the 2283 LSI. So as you can imagine, for the train manufacturer, it's very highly automated, so they're making numbers of benefits with that. This is an unusual project. This is an artist's impression of a 34-meter long humpback whale. It's a sculpture that's been purchased by Dundee Council to put as an installation at their marina. So it's 34 meters long, made from duplex tubes. And the whole structure, as you can see, there are thousands of nodes welded together, predominantly by hand, manual TIG. And the fabricators there, Littlehampton Welding down on the south coast, are using the LSI. They did some trials and liked what they saw, and it's been completely manufactured with this. This should be finished within the next couple of weeks, and it will be on a boat around the coast from Littlehampton up the coast to Dundee. And then finally, we've got a comment from Darren Spalding, a local company to me. He did some trials with the duplex LSI, and there were his comments that he put on LinkedIn for us. So very nice, very good to see. He'd not used it before. He's quite proficient at using duplexes and super duplexes, but he'd never used the LSI version and found it a significant improvement. So that was nice.